Bismillahirrahmanirrahim. Assalamu alaikum dear students. I'm Arif and I welcome you all to the next session on the subject of system programming with Linux. Today is the fourth and the last part on socket programming. In the first part, with a lot of other related topics, we mainly talked about internet domain TCP sockets. In the second part, we discussed the concept along with the proofs about internet domain UDP sockets. In the third part, we shifted the domain and talked about Unix domain TCP as well as UDP sockets. And the title of today's session is Design and Code of Concurrent Servers. Well, this slide shows the agenda of today's session. Before we discuss different design options for concurrent servers, let us understand what happens when an iterative server gets requests from multiple clients at the same time. Well, this slide shows a system call graph we have seen before as well for an iterative stream server. Excuse me. We have discussed that this listen call on the server associate a queue of pending connections while another client is reading and writing data on the socket. So when a client is reading and writing data over here, a request from another client is kept in the queue associated with this listen call. Let us see this. Move on to the terminal and try to understand this concept. Well, right now I am on my Ubuntu server machine and I am Arif. No, this is a Kali machine. Right now I am on Kali machine and the IP of this Kali machine is 192.168.100.21. This one. That's great. Let me show you the code of TCP Eco Server. Remember, this is the iterative version. We have seen it before as well in our previous parts of socket programming. The same program, we created the master or the server socket for connection establishment and associated it with the IP address of the Ubuntu server machine at port 54154. Remember, we are going to run this program on Ubuntu server. We made the bind call to bind this socket address. Then we made the listen call and have a queue of 10 for pending connections. For every incoming request, the server accepts by creating a client socket for data transfer. And well, over here, inside this while loop, the server read the messages from the client and write them back to the client socket until the read returns 0. So the code makes sense. Let us compile this code, tcp ecoserver.c, and let me compile it with the executable name of tcp ecoserver. And let us copy this executable on Ubuntu server with the secure copy command, tcp ecoserver, and let me copy it to the root account, root at 192.168.100.20 in the home directory of root. Okay, so the file is copied over there. Before I go on to Ubuntu server and run this program, let us quickly review the code of the eco client as well, which will of course run on this Kali machine, tcp eco client.c. Well, this is again the same program, receives command line arguments, the IP and the port of the server. So arg v1 contains the IP and arg v2 contains the port. And after populating this address structure, we are calling connect to connect to the server, and then the client is simply reading the std in, writing it on the socket descriptor, and then reading from the socket descriptor and writing it on std out, because this is a simple echo client program. Let us compile this echo client with the name of TCP. Okay, let me name it just client. That makes sense. Okay, so now let's move on to Ubuntu server. Host name Ubuntu server. I am root, and the IP is 192.168.100.20. And right now I'm inside the home directory of root, and we see there the TCP echo server executable is there. Let us run that TCP echo server. So it is running, waiting for an option. Let me move on to another terminal on Ubuntu server, and let us check the status of sockets. netstat-plant, and let me grab TCP echo server. Okay, so Ubuntu server, on Ubuntu server there is only one server socket listing at port 54154 under this process, and it's waiting for incoming connection from any IP, that is 0.0.0.0 from any port. Let us move back to Kali Linux now and run a client program. Clear screen, run the client program, give it the IP of the Ubuntu server 192.168.100.20, and the port number is 54154. So it is running. And let me say hello world. So it works. This is client 1. Let me run another client. 192.168.100.20 at port 54154. Okay, so this is client 2. So it is not responding. We run another client. Client 192.168.100.20 54154. Okay, this is third client. So you see the second client is blocked, the third client is blocked, and let me run another client. Client 192.168.100.20 54154. So all these clients are blocked. However, the first client is working. Sorry for the typos. That's great. Now, if I press Control C over here, so this first client terminates, and this second client is working now. The third and the fourth client are still blocked. Let me press Control C over here. You see the third client has started working now. If I press Control C over here, you can see the fourth client is working over here. That is great. So hence it is proved that this iterative echo server serves one client at a time, and the remaining clients are kept waiting in a queue for their turn. Okay, so let us move again on to Ubuntu server, and let me press Ctrl C to exit this server, and let us check again on this terminal. Let me run this command again, and you see there is no process listening at port 54154. Let me check out the standard echo service which runs under Zynet T. Okay, Zynet T. Let me grab Zynet T. Well, yes. So the init is running, listening on a lot of ports, and note the port number 7 is the echo port. Let us move on to Kali Linux and see what happens when multiple echo clients tries to connect this standard echo service. Is it able to manage multiple connections of clients at the same time or not? Okay, so let me run it. Same IP, but port number is 7. This is client 1. It is working. Over here again, same IP, but port number 7. This is client 2. It is working. And over here, this is client 3. It is working. And over here again, this is client 4. It is working. So all the 4 clients are working. Let me check out. You see, we have 4 established connections, and there is still a process listening at port number 7. These are the data connections on which data is being transferred. Let me press Ctrl C over here, Ctrl C over here, press Ctrl C over here, and press Ctrl C over here. I have terminated all the clients. Let us fall back over here and see the established connection are no more there, but there is still a process listening at port number 7. So that is great. Now let us again, let me clear screen. Fall back to Kali. And let's try writing our own concurrent server. We have a fair idea of what do we mean by a concurrent server now. Let's move back to the slide and see if there are some contents that we need to study. Well, yes, these are the 3 design options using which you can achieve concurrency, or you can write concurrent servers. The first is the multi-process model using fork. The second is multi-threaded model using pthread create. And the third one is the multiplex style using the select system call. Let us see them one by one. Okay, note over here that every time the server accepts a new connection, our client socket is created, and for every new connection the server do a fork and let the child deal with the client using the client socket as a slave process. So this is a slave process that deals with the client, and the server itself wait for the next incoming connection, and if a connection arrives, it again forks, create a child process, and the child process deals with the client. So that means we are creating a fan of processes as discussed in our previous sessions. Well, this slide shows the pseudocode. Note the child process communicate with the client while the parent close the data socket and move up to accept a new incoming connection. So we have a fair idea of using a fork with a concurrent server. It's time to move to Linux terminal and review as well as run a concurrent echo server using fork. Let's come up over here. Let me show you the code. Vim tcp echo server underscore forked.c. Well, this server code is same up till the accept call. There is no change up till here, and after that we have done a fork inside a switch statement. Inside a switch statement we have done a fork, and in case 0, that is the child code closes the server socket, and then in a while loop read and write from client socket, Remember, child has inherited the PPFDT of parent. And when this read returns 0, the while loop breaks and the child process exits. The default case is the parent code. We just close the client socket and break, and that is it. So simple logic. Let us compile this program. TCP echo server underscore fork.c with the name of TCP echo server underscore forked. Okay, so we need to run this on the Ubuntu server machine. So let me copy it. TCP echo server underscore forked to root at 192.168.100.20 and inside the root's home directory. Let us move on to Ubuntu server and check out. Well, it has been copied. Let's run this server. TCP echo server underscore forked. Okay, it is running. Let me change the terminal and check out netstat at port 54154. I don't need the name, so let me remove this PL. Okay, so process is listening over here. Let us move on to Kali now and run a few echo clients concurrently. Okay, so let me run this client at port 54154. This is client 1. It is working. It's great. Let me run this 54154. Sorry, this is client 2 and it is working. Remember, these are working now concurrently. And again, this is third client and we are getting the response, and this is the fourth client. Great, so all are working. Let's move over here and check out the status, and you can see we have 4 established connections and all from the Kali machine. And we still have a socket which is in the listen state. So what we need to do now is we need to check out the 3 established connection. Fine, and if I come back over here and close these connections one after another, so all the connections are closed now. Fall back to Ubuntu server, check out. That is great. Let us check the status of the processes. Oops. There are 4 zombie processes or defunct processes, and this happens because their parent process has not waited for their termination. Well, we can put a wait call in the parent code which will make the parent wait till child terminate, but that will make the model iterative. One solution can be write down code for reaping of the child process inside the signal handler of sig child, and we all know that when a child process terminates, the kernel sends sig child to the parent, and inside that signal handler we can do the reaping. Right now let me kill them manually and fall back to the code again. Let me kill them. Let me send a silver bullet to 9525. This is a defunct process. Let me check out. I've sent a signal to this, but it has not died. 9525 process is still running. Well, yes, you're right. You cannot kill a zombie process even with a silver bullet. So what to do? Let's kill its parent and make it an orphan, and let systemd do the rest of the job. So let me kill the parent, and the parent is 9521. And now if I check out, the parent is gone and the orphan processes are also gone. So let us solve the issue by adding a few lines of code in our server program over here. Let me clear screen and let me vim tcp echo server underscore forked.c. Okay, so we need to register a signal handler, and we all know how to register a signal handler. Inside main, we just have to say signal and chld sig child, and let me name the signal handler as Reaper. Excuse me. And let me write the code over here. Void Reaper in sig. Remember, we have already done this signal handling before, and you know. And let me just write down single line of code, that is wait PID. And let me say -1. -1 means wait for any child process. And let me say the second argument as null. That means I am not interested in the return status of the child right now. And the option is 0. Okay, fine. So that is it. Let us compile this program again. TCP echo server underscore fork.c with the name of TCP echo server underscore forked. Fine. And let me run scp, yes, and let me copy it over there. It is copied. Let me come up over here, clear screen. Let me run this code. Server is running. Let me check status. Okay, it is listing. Come back over here, run multiple clients. Let's suppose /@ 192.168.100.20.54154 working. Run another client, working. Run another client, it's working. And over here you can see we have 3 established connection, and of course there are 4 processes. Let me show you this as well. The 4 processes, we have 4 processes, all are running perfectly fine. Let me kill this client, let me kill this client, and let me kill this client as well. Let's fall back and check out. There is only one socket listing and we have only one process. There are no zombies. So we have solved the problem of zombie process. Let me press Ctrl C to terminate this server. And let us fall back over here. Okay, so now we are done with achieving concurrency using fork. Let's fall back to slides and see the second model to achieve concurrency. Well, this slide shows the pseudocode which creates a child thread for each incoming connection to achieve concurrency. Please note that you should create a detached thread. As if the parent thread joins the newly created thread, the model will become iterative again. So we need to create a detached thread, and we know how to create a detached thread. Excuse me. Okay, let us now move on to the Linux terminal again to review the code and run our concurrent echo server that use the pthread creates library call. Okay, let me vim TCP echo server underscore threaded.c. Well, this server code is also same up till the accept call. Over here, it is the same code as we have discussed before many a times. This is a piece of code in which I am going to create a thread. Well, dear students, each time when accept returns, we are creating our detached thread. Each thread will execute the TCP echo D, this function, and the client socket file descriptor is passed as an argument to the thread function. And this is the code of the TCP echo D, that is a thread function, which is simply reading and writing on the client socket descriptor in a while loop until read returns 0. So let's compile this code. GCC TCP echo server underscore threaded.c with the name of TCP echo server underscore threaded. Fine. Oops. Let me link it with LP thread, the threading library, and let us copy this. TCP echo server underscore threaded dot, okay, threaded to root at 192.168.100.20 in the home directory, and I'm not going to tell you the password, so it is copied. Let's move on to Ubuntu Server. Check out, the executable is there. Let me run it. Underscore threaded, so it is running. Let's check the status of the port. So a process is listening over there. That's great. Let's move now on to the Kali and run few echo clients as we have done before as well. Let me run a client from here. Okay, this is client 1. Okay, that's great. And this is client 2. So this is working. And this is client 3. So this is working. So all the 3 clients are working. Let's check the status over here. So we have 3 established ports. Great. And if I do a PS-A, you can see there is only a single process because we are now doing with the multi-threading. Let me quit this client. Let me quit this client, and let me quit this client. Fall back over here. Check out the status. That is great. And if I do PS-A, we still have 1 process. Let me kill that process and go PS-A. It's all great. So fall back. So far so good. Now let us move on to the slides again and see the third and the last model to achieve concurrency. And for the third model, we are going to use the select system call. Right, dear students, we have not studied this call in this course previously, so let me quickly touch upon some important aspects of this system call so that we can use it for writing our concurrent echo server. Well, dear students, a process sometimes expects input from 2 different sources, but it doesn't know which input will be available first. For example, consider a process trying to read from source A, but input is only available from source B and the process blocks. One solution of monitoring multiple file descriptors is to use a separate process or a separate thread for each descriptor, as we have recently done. And the other method is perform I/O multiplexing, which can be done using either the select system call, which appeared in BSD Unix, or the poll system call, which appeared in System 5 Unix. Nowadays, both are required by single Unix specification version 3. Well, the select call allows a program to monitor multiple file descriptors until one or more of the file descriptors become ready for some class of I/O operation. And a file descriptor is considered ready if it is possible to perform a corresponding I/O operation without blocking. Well, the select call is given 5 arguments. The second, third, and the fourth argument are 3 descriptor sets of type fd_set. The second is the read file descriptor, a set of read file descriptors to be tested to see if input is possible. This is a set of write file descriptors. to be tested to see if output is possible. This EFDS is the set of file descriptors to be tested to see if exceptional condition has occurred. And of course, this doesn't mean an error condition. Well, this first argument must be at least one greater than the largest file descriptor in all the three descriptor sets to achieve performance gains. You can put it to the maximum number of entries in a PPFTT. And this fourth argument, the last argument, is the timeout value, which is a value that forces select to return after a certain time has elapsed, even if no descriptors are ready. That is a non-blocking IO. A null over here means block indefinitely. Well, the select call returns one of the following: a -1 in case of error, a 0 indicating that the call timed out before any file descriptor became ready, and a value greater than 0 indicating the total number of ready file descriptors in all the three descriptor sets. Well, the descriptor set is a data type that is implemented as bit fields in array of integers. A bit in our descriptor is 0, it means that the corresponding descriptor is not ready. And if a bit in this descriptor set is 1, that means the corresponding descriptor is ready. So instead of using bit handling operators, you can use these 4 macros. This first macro fd0 initializes the descriptor set to all zeros. This fd set include the given descriptor fd in this descriptor set. This fd clear exclude this descriptor fd from this descriptor set, and this fd is set is used to test if this descriptor fd is in the descriptor set fds. It has a value of 0 or 1. It returns 0 if fd is not in the set and non-zero otherwise. Please do see the man page for more details, and let me move on to the Linux terminal to review the code and run a concurrent echo server using the select system call. Clear screen, vim tcp echo server underscore select.c. Okay, so once again the server code is same up till the listen call. Up till here there is no change. Oops. Okay, we have created 2 descriptor sets, RFDS for data connections and AFDS for accepting new connections. Then we have used fd0 macro to clear R entries in these 2 descriptor sets. Then we have used fd set macro to add the server socket descriptor in the accept file descriptor set. Well, this get d table size is used to get the file descriptor table set size. And then we have used memcopy to copy both these in this RFDS. This AFDS is also copied in this. And then we have used the select call. Well, the first argument to the select call is the largest file descriptor in all the 3 sets. It should be. I have kept it to the size of PPFTT to cater for maximum possible connections. The second argument is a set of descriptors to be tested for input. The right descriptor set and the exceptional condition descriptor set are kept null. And the timeout argument is also kept null to block indefinitely until a descriptor set is ready for IO. Well, when select return, I'm using fd is set macro to test if the server socket fd is set in the RFDS. If yes, I am calling accept. And then using fd set macro over here to add the client socket descriptor to the accepted fd set. We are done up till here. Well, then I am entering in a loop checking for a ready descriptor which is not a master socket descriptor. but it is there in the RFDS, read file descriptor. On finding such a descriptor, I am calling TCP echo D function and passing that file descriptor to the function as argument. And this is the code of that TCP echo D function. Hope this code is making a bit sense now. Let us compile this code. GCC TCP echo server underscore select.c with the name of TCP echo server underscore select. So it is done. Let me copy it to the executable to Ubuntu server. /TCP echo server underscore select. And let me copy it to root at 192.168.100.20, the home directory. Successfully copied. Let us move up over here and check out whether the server is there, and let me run it. TCP echo server underscore select. So it is running. Let us move on to another terminal on the Ubuntu server and run netstat -ant, and let me grep 54154, and a process is listening on this port. Let us move on to Kali now and run few clients concurrently. /client 192.168.100.20 54154. This is client 1, it's working. Let's run another client. Over here, this is client 2, sorry, 2, so it's also working. Let me run a third client. And this is also working. So all the three clients are working concurrently, and if I check out, we have three data sockets and we have one master socket which is still in the listening mode. So that is great. All three clients are connected to the echo server and running successfully. Let us kill them. Kill this client, kill this client, and terminate this as well. Let us move on to Ubuntu server, check out. So that is great. That is great. And let us terminate this TCP echo server as well. And fall back to slides again. So that's great. We have done all the three models of achieving concurrency using fork, using pthread create, and using the select call. Well, dear students, we all know that concurrent servers are used to reduce the average response time experienced by a client. However, the need of a concurrent client is not so obvious. Consider a TCP echo client which expects input from two descriptors, one from the user via keyboard and other from the client-side socket that is connected to the server-side socket. A user may type some text using the keyboard anytime, and the server response from a previous client message may also arrive at the client-side socket descriptor at any instant of time. Since the two descriptors become ready asynchronously, so you can implement such concurrent clients by using the select system call. Other than echo, you can have concurrent clients like SSH, Telnet, FTP, HTTP, and so on. Okay, at the end we have the assignment. Well, dear students, if you have programmed the iterative version of netcat utility as an assignment given at the end of video session number, I think 35, try enhancing it so that it can act as a concurrent tool using any of the three models discussed in today's session. So with this, we come up to the end of today's session. I have tried to cover all important aspects of socket programming in these 4 sessions. Inshallah, in the upcoming sessions, we will discuss the concept of buffer overflow, which is probably the last topic, and we will see how we can exploit an application suffering with this vulnerability to get a remote login session. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. Happy learning and Allah Hafiz.